And that pretty much gives you a snapshot of the universe, how it was a couple of 100,000 years after the Big Bang, when this radiation began to flow freely. And so given this, given the fact that the universe was hot, given this radiation exists, it is sufficient as observational input to conclude that if Einstein's theory of relativity is correct, then there must be a beginning of time. It's unavoidable. That's the thing. That's the real pain for Einstein, right? It was unavoidable. You could prove on the basis of his own theory that it predicted its downfall. And so now he really had a problem. Because in the case of black holes, you might say, well, fine, okay. I am just not interested in the inside of black holes. I'm not going to think about it. I'm outside. It's your problem. But in the case of cosmology, if there's this issue with the Big Bang, it's about you. This is our past. This is our identity. And without getting a grip on the Big Bang, fundamentally, we don't know where we come from. We are just the remnants of the physical conditions on how our universe came to be. And the real problem is that we appear to live in a fucking special universe. We appear to live in a universe which is mysteriously, delicately fine-tuned in order to bring forth billions of years after the Big Bang something complex like Christiania, right? I mean, all these collectives here. So there must be something special about the Big Bang in order to get the universe going in just the right way that you end up with something which can harbor life, which is habitable. Gravity must be weak, because otherwise we would be crunched. 3 space dimensions is very handy. If you had 4 or 5, you wouldn't have stable planetary orbits. We have a bit of dark energy, but not much. If we had a lot, stars would never have formed, and so forth. The list is long of features of our universe which seem just right. And so the question about the completeness of the laws of science became much more important when the whole enterprise was applied to cosmology and to the Big Bang. And this is the core of Hawking's thinking. That's the real starting point for my conversation with him. It's what defined his thinking for decades, and in fact, it's nicely again, Hollywood. It's nicely pictured here in this movie. Huh?
And then, of course, we have chapter 4, this black hole at the beginning of time.
Space-time singularity.
Indeed. It's brilliant. Brilliant, Stephen. Superb. Therefore, all there is to say is well done. Or perhaps I should say, to be more precise, well done, Doctor.
Bravo, Stephen.
An extraordinary theory.
Thank you.
So what next?
Prove it. Prove with a single equation that time had a beginning. Wouldn't that be nice, Professor? So one simple, elegant equation to explain everything.
Yes, it would. It would indeed.
Thank you.
So that was basically his central goal for the rest of his career. We move backwards in time from the present day all the way back to a few 100,000 years before the Big Bang, where we had a hot universe radiating, which we see now. But then what? Ultimately, Einstein's theory breaks down. And in fact, when you do so, following the equations of Einstein and insisting on their validity, at some point you reach a phase in which the evolution becomes chaotic, and in which our evolution here gets mixed up with all sorts of different possible universes. Basically, if you insist on Einstein's theory backwards, you end up with a multiverse. An ensemble of possible worlds, like bubbles in boiling water, of different kinds, perhaps even with different local laws of physics. And again, basically, in essence, a breakdown of predictability. Because good, fine, and now what? Where are we? And what should we observe? And in what kind of world should we find ourselves? And so we did another thought experiment together now, in order to get a grip on this. And the thought experiment was, all right, let's go backwards, but let's not insist on the validity of Einstein's theory. Let's think about the whole universe from a quantum perspective. When the universe is large, this doesn't really matter. But it turned out when we went backwards in time, that quantum theory became important, and that the evolution further backwards is not governed by Einstein's theory, but just like black holes, that the notion of time evolution backwards was basically no longer happening. The whole evolution is turning into, again, a hologram. But in this case, it's not space which is disappearing, as we saw in the case of black holes. It's the further time evolution which is disappearing. And so we were led to a picture in which, instead of getting into a huge mess of a multiverse with infinitely many possible worlds, we are led to the picture of, wait a minute, we've pushed Einstein's theory too far. It's like trying to use it to go inside black holes. If you do, you end up with really a kind of bifurcation of reality in many realities. Similarly here, if you go too far, you're really pushing Einstein's theory where it doesn't apply. But rather thinking about it quantum mechanically, and you see that the world more and more becomes delocalized, fuzzy, holographically represented. And what is that hologram? It's a kind of ultimate horizon to our reality. It's a kind of boundary, a kind of very abstract state from which you gradually our universe in familiar notions of space and time emerges. The way Stephen described that holographic state is as follows. The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. Now the key question, this is all good and well, fine, okay, we get some different handle on the Big Bang. Time, we lose our notion of time basically on our way to the Big Bang, and therefore avoid that catastrophe that you get when you extrapolate Einstein's relativity. But the key question is, of course, well, now what? What kind of universe can emerge from such a holographic origin? And it turns out that that hologram as a model of the Big Bang predicts a very special universe. It can only get universes going which come into existence in time, so to speak, in a phase in which the initial expansion is very, very rapid, much more rapid than it is today. We call this cosmic inflation. So somehow from that holographic, delocalized, fuzzy quantum origin, say, time, or the dimension of time, can only crystallize in a way that gets the universe going in an extremely rapid, short burst of expansion, so to speak, inflation. But that has a very, very special effect. It has the same effect as what we discussed earlier for these black holes. If the universe expands very rapidly, these virtual particle pairs, now, because of the rapid expansion of the universe, they're going to be torn apart. They're going to be converted again into real particles. And look what happens. The radiation, the afterglow of the Big Bang, won't be completely the same anymore. These real particles, they manifest themselves as flickering. The radiation begins to flicker, begins to change from one place to another. These different colors here represent temperature difference, temperature fluctuations in the Big Bang afterglow, which is a very definite prediction of having an origin which comes together with inflation. So now what? Let's say, aha, good. So there's an experiment. Now we can look and measure the radiation. This was the picture I showed you in '65. But that picture was taken by engineers, right? Who, furthermore, they weren't looking for it. Since then, physicists have gotten their act together and have done their own measurements, more precise, and indeed, the afterglow of the Big Bang is not what people initially thought it is. It does flicker. It's not exact. It doesn't have exactly the same temperature everywhere on the sky. There's a pattern of fluctuations. And cosmologists continue to study that pattern of fluctuations in order to learn more precisely how that very early phase of inflation happened. Now, those fluctuations are important. Those fluctuations are crucial. They're basically you and me. Those fluctuations, which themselves arose from the amplification of these virtual particle pairs at the universe, at the Big Bang, at the origin of our time, those temperature fluctuations in the afterglow gradually evolve millions and millions and billions of years later in the stars and the galaxies we see today. If these fluctuations had not been there, if the Big Bang afterglow would have been the same everywhere, same temperature, then we wouldn't have been there either. This is an amazing synthesis. It's the beauty of cosmology, to connect our existence today, here on Earth, basically to the hologram at the origin of our world. It's a kind of evolutionary synthesis which brings Darwinian evolution on Earth and chemical evolution throughout generations of stars into one grand cosmic scheme. And furthermore, that evolution is not a pre-given. It's our observations today which really shape, which really decode the hologram at the origin of time. It's above all a human adventure. By studying the Big Bang, we learn a lot about ourselves. And indeed, Stephen was above all human too. Thank you.